So I'm delighted to welcome Professor Joe Bovy from the University of Toronto, who's going to talk to us about the Milky Way in the era of large astronomical surveys. Thank you.
All right, there we go. All right, well, thanks very much for inviting me to give this talk. So I will talk about what we've been learning about the Milky Way in the era of large surveys. So the Milky Way, I think, is a really, it's a really central object in astrophysics. It's where we see like how stars form. It's where we see exoplanets around other stars. It also has a lot of things to say about kind of our cosmological environment and how galaxies form. So I think the Milky Way is really a really fascinating object to study, and so it's been studied for like more than 100 years in detail. But what's really new in the last, decade or so, and is really accelerating, is that we now have very large surveys of stars in the Milky Way. And so that kind of changes how we do science, but it also really accelerates the progress that we get. This is mostly currently being done by the Gaia mission, which is producing observations of more than 1 billion stars. But there's also a large amount of other surveys that are associated with this. We had a great specialist discussion today that was organized by Daisuke Kawada, Dennis Urkel, Pael Das, and myself, where we talked about a lot of the exciting results that are coming out of the Gaia data, and it's really amazing to see all the things that we thought we could only kind of study like with pen and paper and on computers, that we can actually now observe like really subtle dynamical effects with actual data from the Gaia mission. So I'll give somewhat of an overview of what it's like to do astrophysics in this era of large surveys. To start, I'll just take you on a little journey through the Milky Way to remind you of what the structure of our galaxy is. So we live in a spiral disk galaxy that's very similar to many other galaxies in the current universe. So we're just going to zoom out from the center. So what you see here is there's stars are very centrally concentrated at first in the center of the galaxy, and here, if you get on scales of a few hundred parsec, stars form a kind of spheroidal distribution. It's called the galactic bulge because it kind of bulges out of the disk. This is what we see in external galaxies as well. If you zoom out then on the scale of 10 kiloparsec or so, most of the stars in the Milky Way form a very flat disk. That's also where the sun lives, and that contains almost more than like about 70-80% of all the stars, with most of the other ones being in the bulge. The stellar disk is surrounded by there's gas in the disk as well, and surrounding the disk is a much smaller component of stars. It's called the stellar halo, which also includes globular clusters and such. And then the entire stellar distribution is contained within a much larger dark matter halo that is much more massive, and that kind of sets the gravitational potential that everything is moving in. So let's jump in here and look in more detail at the Milky Way. So here again, just as an overview, a top-down view of the Milky Way over here. The sun sits about halfway out from the center, very close to the midplane of the disk, and this is what it looks like kind of on the side. So I'll be talking today about what's going on kind of in the central part of the Milky Way, and also in particular what's going on, like what the state of the disk is, and what's going on in this stellar halo, like what we can learn about that. So we'll just cover all of the major stellar components of the Milky Way in just the next 20 minutes. So as I already said, it's a really exciting time to be a Milky Way astrophysicist, because there's just lots of data from lots of large surveys. In particular, I work a lot with high-resolution spectroscopy. So this is if you take the light from a star and disperse it at very high resolution, you can see, for each, these are just stars in a few open clusters. You see really many details, many absorption lines that allow you to measure the abundances of many different elements in the atmospheres of stars. We have these now. It used to be just a few decades ago, we could do this for tens of stars, and people would write papers making lots of conclusions about the structure of the Milky Way based on just tens of stars. You could just publish them in a table in your paper. Whereas these days, we have now in the 2010s, we have hundreds of thousands of stars with surveys like Apogee. This is data that was just released in the 16th data release of the Sloan Digital Sky Survey. As you see, we can now plot these amazing HR-like diagrams with hundreds of thousands of stars. And in the next decade, this will get even more. We'll get like another factor of 10 or so of these really detailed observations of the structure and the chemical makeup of stars. I already mentioned the Gaia mission, which is measuring astrometry. So in particular, parallaxes, which give us distances, and proper motions, which give us the motion on the sky. So this is the parallactic effect with the proper motions, where you just see the fact that the Earth goes around the sun leads to a parallax ellipse, and then the proper motion leads to a secular shift, which allows us to measure both the distance to the stars, or the inverse of the parallax, and how stars are moving on the sky. So this is a really long history. This is, the ancient Greeks were doing astrometry in many ways, and so you can trace the increase in the accuracy all the way from thousands of years ago until the first measurement of a parallax by Bessel, just about 150 years ago. And now, just 20 years ago, we had a survey like Hipparcos, which is also a space mission, very similar to Gaia, where we had parallaxes for about 100,000 stars. And now with Gaia, we've made an enormous leap where we now have 1.7 billion stars, which we have this type of data. So that's a really at much higher precision. This is 10 microseconds versus Hipparcos being about 1,000 times less accurate. So we can study, whereas this allowed us to study stars, within a few tens of parsec, up to about 100 parsec from the sun. We can now go kiloparsecs in the galaxy. There's similar advances in different types of surveys, so just taking photometric surveys, just taking pictures of the sky. They're like increasing, especially with LSST, starting very soon. That will also lead to billions and billions of stars that way. And astroseismology, looking at oscillations due to in the structure of stars that allow us to measure things like masses and radii of stars, has a similar revolution that's been going on. So this is the era of large surveys. So I just want to give you a sense of a few things we can do. So I'll focus on a few big questions about the Milky Way's formation. In particular, what the physical state was of stars and gas in the history of the disk. Like, what was it like in the early history of the disk when the disk first formed? What is it like today? And also want to talk about what fraction of stars was actually born outside the disk. So this is this stellar halo, which is this kind of spherical distribution of stars that surrounds our disk. There's very few stars, as a fraction of the total, but because it's very interesting to understand where these stars actually come from. So I'll talk about that a little bit, and then also want to focus on the inner region of the Milky Way, where we think the Milky Way has a bar. We want to know, what is the structure of the bar? How did it form? What is it doing? How is it affecting the rest of the galaxy? How do these things all fit together? And I also want to focus on a few kind of challenges and kind of new things we can do in getting the most out of these large surveys. So in particular, I talk about how we use fast machine learning tools to really revolutionize the analysis of these very large data sets, because we have to be able to process hundreds of thousands of data points for stars. And for example, one of these high-resolution spectra from Apogee, we have them for 500,000 stars, but each one is 10,000 points along a spectrum. So these are really enormous data sets, and these will be growing, as I said, much. So we need really fast tools to be able to do this. And then also, I think it's very important to keep track of observational biases in how we survey the stars. Like, if we want to really understand our galaxy, and we have so many stars, we need to really understand the biases in our sampling of the galaxy. So I'll start in the first part, just focusing on this inner part of the Milky Way and how we can map the inner Milky Way using the Apogee data, which is high-resolution spectroscopy, the Gaia astrometry, and a technique called deep learning. So why do we need something like deep learning? So I already showed a high-resolution spectrum. Here's a full spectrum from Apogee for 3 stars. So you see there's lots of data here. And so the traditional way would be for a spectroscopist to look at each one of these stars in great detail and look at each of these lines. People would know exactly which are good lines and which are bad lines, and they would analyze each of them with great care, so that they can drive things like the temperature of the star, the gravity of the star, the overall abundance of metals, in stars and the relative abundance of different elements, such as on the ratio of oxygen to iron and such. So this is why this was something you could do in the age where you had tens of stars or hundreds of stars. But if you have hundreds of thousands of stars, this is of course impossible to do. You also can't really get things out like the luminosity or the mass or the age of a star because we don't really have models for how these things actually depend on the luminosity or the mass of stars, even though we think that there should be information about these quantities in these spectra. So this is where deep learning comes in. So what you do with kind of machine learning and deep learning in particular is that you take just a whole bunch of these spectra. We now have these for many, many stars. And we can analyze them with kind of traditional methods for some of these stars. But then we can teach a computer, essentially, to tell us what is a function. Give me a function that will, if I run the spectrum through it, give me the temperature, the gravity, the amount of metals, and the different abundance ratios for all of these stars. And so why this is called deep learning is that these functions are very flexible functions that are just represented as a neural network, which is essentially just a sequence of layers where there's a kind of linear matrix multiplication in each layer with a little bit of a nonlinear function in between. So they're a pretty simple structure, but you just add many of these layers, and you can show that can just become an extremely good function interpolator in some sense. And so you can train these very easily. There's lots of work on this area, and this is what people are trying to use to make cars drive themselves and such. There's an enormous amount of investment in this from industry, and so we can capitalize on some of that technology in astronomy as well. So we can learn very complex relations between the input and the output just from a training set, and you need a large training set, but we have that from these spectroscopic surveys. And then these are really fast because then you just have a function that you just run through and you just get out all the parameters for your stars. Also, if you have a good training set and there's some sort of plausible physical connection like between the spectrum and the luminosity of a star, you can even train relations for which we don't actually have physical models. So we can learn how to get from a spectrum what the luminosity is or what the age of a star is, even though we couldn't write down a physical theory that we really believe. But if we just think that it's there, we can just learn what this should be in a data-driven manner. So that's another great advantage. So we in particular, this is led by my student, Henry Leung, who's in the audience here. We have a package called Astronomical that is just a general framework for doing this kind of learning of models, but specific to astronomy. And we've done a few applications. So one is this kind of neural network to get elemental abundances and parameters of stars from these high-resolution spectra. So that's what I've been talking about mostly. But then we also have a similar network that will give us the luminosity of stars. And then if you combine them with photometry, you can get distances to stars. So this is trained on, the first one is trained on an apogee data. The second one is trained on apogee plus Gaia data because the Gaia data gives us luminosities for stars because Gaia has parallaxes for lots of stars. And then we also have a similar one that can give us the ages. So it allows us, for example, it's not very clear in this picture here, but this is, for example, the distribution of stars in an apogee sample in the space made up of metallicity and the ratio of oxygen to iron. This is one of the typical spaces that we look at, whereas this is kind of more traditional method. You see a lot of the structure is smoothed out, but we can actually get much more precise data coming out of these neural networks and see a lot more structure in this, and particularly see that there's this kind of upper sequence and lower sequence, which is not as clear in the traditional methods. So these can even do much better in some ways than the traditional methods, which is a little funny. And this is a comparison with Gaia, so if you're near the sun, Gaia gives you, the sun is over here, this is a top-down look at our galaxy, so we're looking down here on the disk. Look, near the sun, Gaia, because it can measure parallaxes, gives us a more precise distance, but the parallaxes, they get smaller and smaller as you get farther and further away. So at some point they become too noisy, but our neural network, because it just takes a spectrum and gives us a distance from that, can do much better. So at large distances from the sun, we get much better distances from these kind of methods than we do from Gaia. So here's an application to looking at what the structure is of the inner Milky Way. So we have, from apogee, we have about 500,000 stars with high-resolution spectra. Gaia gives us parallaxes, which is like 1/distance in proper motions for about 1 billion stars. And then if we use deep learning, we can get better distances, we can get better abundances that we normally get from apogee, and we can also get ages from these stars as well. So that allows us to make maps of the age, the metallicity, and the ratio of oxygen to iron for stars in our galaxy. So the sun is right here. So this is the inner galaxy, this is the outer disk. These are all stars very close to the center of the disk. So this is just, I'm going to show you what kind of improvements we get if we apply deep learning to these data. So this is just if you take the Gaia distances without using deep learning, and you use the abundances that apogee gives us. So no deep learning in this slide here. So you see that there's, things seem to be older in the inner galaxy. They're more metal poor, but it's not very clear. It seems kind of, circular here. So it doesn't look like there's a bar there. So we can first put in the better abundances that we get from deep learning. So things kind of sharpen up a little bit. We see trends a little more clearly. Things are more metal rich maybe than they seem at first. And you can kind of see a bar appear here. And then if we use actual distances that we get from deep learning, we see much like that this inner galaxy really comes into view. And we can suddenly see that there seems to be a bar going this way here that we see in all of these different components. If you overlay, this is where we think the bar should be just from looking at the numbers of stars in the inner galaxy. But we see now also that in age, you see clearly this bar-shaped feature in metallicity and in oxygen to iron as well. So that's really this improvement, especially in the distances that comes from using these machine learning methods. And so from this we see clearly that the bar seems to be very old. It's certainly made up of very old stars. The most obvious interpretation is that the bar is old and that it formed about 8 billion years ago or so. Otherwise, so it's more metal poor, and it's enhanced in these alpha oxygen to iron compared to the disk. So these are all stars very close to the disk. But if you look at how these change, how this in particular changes the metallicity in the bulge, you see the same exact trend as we see in the older part of the disk. So it seems like the bar is just some part of the old disk that was rearranged into a bar-shaped feature. And that's what we expect from the dynamical evolutions of galaxies, but we can see this now directly with these kinds of maps. We can also look at the kinematics of stars. So here we're looking now at velocities in the plane of the galaxy. So this is the rotational velocity, so how stars are moving around in this way. This is the radial velocity, so how stars are moving in and out in the galaxy at different positions. And this is the rotational frequency, so just this divided by the radius. This is, again, if we just use the Gaia distances. So, it seems a little messy. So again, kind of, the rotational velocity goes down, but there's no clear bar here, and there's not, this is a bit of a mess here in the radial velocity. But if we use the better distances, we see that this actually looks more like a bar again, and in the radial velocity we see this part of a quadrupolar signal that is exactly what you expect if the bar is pointing along this way. So we see the bar, we see exactly these patterns that we should see from a bar in the Milky Way, and if you compare it to a simulation, for example, you see that simulations look very similar. So just by having these better distances, all of these trends suddenly completely come into view. So we see very clearly these expected motions. These are also great data because now people have been working on how fast does the bar rotate in the center of the galaxy. The bar should rotate as a solid body, but it's been very hard to figure out how fast the bar is rotating. But if we have data like this, we can actually just use the continuity equation, just the fact that stars should flow in and out of volumes without any stars being formed or dying, because these are very long-lived stars. So just that physical principle alone, we can rearrange terms so that we can just take these maps and turn them into a measurement of how fast the bar rotates. So that gives us a period of about 150 million years, 41 kilometers per second per kiloparsec in the units that we normally use. And so we see that the bar is really rotating as a solid body in the center of the galaxy. So this agrees with more complex modeling people have done, which is shown as these data points here. We are measuring the pattern speed more in the outer part of the bar. Previously, people have measured it in the inside of the bar. They all agree, so that's again showing directly that the bar is actually rotating as a solid body. So this is all because of Gaia, but also because of these new ways of analyzing the data with machine learning methods. So let me move on to talk a little bit about how we can map the Milky Way with star counts in multiple dimensions. There's changing gears a little bit here now. So most of what we know about the Milky Way comes from actually just counting the numbers of stars in different parts of the sky as a function of position. So Herschel did this here, made the first map of the Milky Way, a very famous picture here. Kapteyn did this like 100 years ago and came up with his universe, where the sun was roughly at the center of the Milky Way. He says, before we knew there were other galaxies, essentially. So this is how people have been building models for the Milky Way, and it's in many ways still what we're doing today with surveys like Gaia. But now we have velocities, we have ages, we have metallicities for stars, we have all these abundance ratios. We have this for very large numbers of stars. So now we can go beyond just counting stars as a function of their 3D position and making 3D models for the Milky Way, but we can also measure stars as a function of their velocity, as a function of their age, as a function of their metallicity, and so create very multi-high dimensional maps of the Milky Way. And that's essentially what we then have to work with in terms of interpreting in terms of galaxy formation and evolution physics. Now there's one problem, especially if you use a survey like Apogee, which is that you see that this is the Apogee data, just color-coded on top of a picture of the galaxy and color-coded by their metallicity. But you see immediately that there's all these spikes in the data. So those aren't really there. That's just because this spectroscopic survey is just saying, I'm going to look at stars in that part of the sky, now I'm going to look over there, but I'm not doing all the ones in between. So there's a very large sampling effect that's going on. And so here's some work by Ted Mackerath, one of my collaborators. This shows for Apogee kind of how complex this selection really is. So there's first of all these little fields, all these spikes, which is where the discrete points in the sky where we have actually looked at stars. And then because we only look at a fixed number of stars, like a few hundred stars in each position, well, in some parts of the galaxy, there's thousands of stars that we could have picked. In other parts of the galaxies, there are only a few hundred stars. So the completeness of our survey is a very strong function of where we're looking. So you see, if you're looking, the plane of the galaxy is here at the z equals 0. If you look out, it's very complete. The color coding here is completeness, so it's above 25% complete. So you're picking up almost all the stars that are really there. But if you're looking at the disk, well, there's so many stars there, and we're only picking up a small number. We are very incomplete. And so the things that you don't see, you have to take into account as well. So you have to take all of this into account. Another issue is extinction. There's highly variable extinction in the Milky Way. This is just a map of the extinction out to about 5 kiloparsec or so. So if you're close to the plane of the Milky Way, lots of stars are obscured due to extinction due to dust. And so the fact that we don't see stars when we look very close to the midplane, well, that could be that there aren't no stars there, or it could be that they're just extinguished by dust. And so we have to use models for the dust extinction as well. So it becomes very complex to really make models of the disk. But we have done this, and so I just want to give you a taste of some of the things that we've learned about the structure of the disk. So one thing that we like to do is that we take the data and we bin it by metallicity and by this ratio of oxygen to iron, which are the kind of two main metallicity measurements that we use in the Milky Way. And then you see that the structure of the disk is really a strong function of these abundances. So these are kind of like radial profiles that you get if you split up the disk in this way. So these are stars that we think are old. They have high ratios of oxygen to iron, which means that they must have formed early in the galaxy. And those seem very centrally concentrated. They just kind of fall off as exponential functions. And they're very similar for all of these different populations of different metallicities. Once you look at more metal-rich stars, younger stars, you see that this doesn't quite continue, but there's this kind of break in each of these radial profiles. So really it seems like the disk is made up of donuts once you go to this part, where the outer disk is made up of these big donuts of a given metallicity, and then the inner part of the disk is made up of smaller donuts. Normally I make a joke about what this is, but I feel like this is not the right venue for that kind of joke. So this kind of leads us to thinking that there's two stages in disk evolution, but there's this turbulent stage that kind of creates these populations where everything's very well mixed. So you get these very simple populations, and everything is the same no matter what the metallicity is of stars that are formed. whereas there's a second stage that's much more quiescent, where the disk is actually stratified into different rings. And these rings each have different metallicities, and they each have like a separate equilibrium, and those go all the way to the outer disk. I'm just going to skip maybe the next slide because I think I'm somewhat running low on time. So I'm going to talk about the halo briefly. So the halo is this spherical component around the Milky Way. So it doesn't make up many stars. We measure it to be about 3% of all stars, but it's very interesting because if you look at it, there's lots of interesting stuff going on. This is a map of stars in the Milky Way halo from Vasily Belokharov's work. And you see it's not very smooth. It's like made up of like remnants from satellites that are merging, like the Sagittarius stream that's currently merging in. There's lots of other streams. And so it seems like the halo is a repository of external galaxies merging with the Milky Way. So with the same apogee data, we can actually try to do this very quantitatively to see what's going on in the Milky Way disk. And so we can map, again, cutting the sample of stars in this plane of metallicity, and in this case magnesium to iron, which is similar to oxygen to iron, and we can just measure how much mass is there in different components. And we also split this up by how radially the stars are moving in the Milky Way. And so we find that actually about 25% of the stellar halo seems to be stars that are coming from the disk, so they were somehow kicked up out of the disk, maybe by mergers, and that have now created this halo, where 75% of stars do seem to be brought in by external galaxies. It seems like the largest single merger has been a pretty minor merger, because if you look at, you can kind of extract from this what the largest single merger is. So it seems like we haven't had a very large merger, just a bunch of small mergers. And so most of the halo is an amalgamation of multiple systems, not just a single system. So I'm going to go to my conclusion slide because I think I have very little time. So here's just some, of my conclusions. I think it's really a golden era for galactic archaeology. It's a great time to be working on this in this field, and we're learning a lot about galaxy formation, also about the nature of dark matter and things like that from studying the Milky Way. And in particular, I've highlighted a few new insights. The fact that the Milky Way history is largely quiescent with only minor perturbations by external things like satellite mergers. It seems like the disk has these two stages, where there's a kind of early turbulent stage that's followed by a later quiescent stage. And the bar is really kind of a major component of the Milky Way. It extends far into the disk, and it's the way that it's rotating means at that speed it really should be affecting the velocities of stars in the disk quite a bit. So it's something we really have to take into account if we study the Milky Way. Thank you very much.
Thanks very much for that very interesting presentation. So we have time for a couple of quick questions from the audience. Yes, at the back here. You just hang on for the microphone coming your way.
In the middle of your talk, you showed the metallicity of alpha to ion, the metallicity of bar area.
Right.
In a classical observation with limited sample, I thought the central part of Milky Way was most metal-rich, like body's window.
Yeah, so it strongly depends on where you're looking. So you see that there is a more metal-rich part that's over here. So if you're looking outside the bar in the inner part of the galaxy, it is more metal-rich. And as you go to higher, larger heights, like in Bode's window, it might also be more metal-rich. It's very specifically the bar that is metal-poor. Yeah, it is a bit of a puzzling observation. But it does seem to agree with at least some simulations that this is. And so it's very clear, and it's very hard to see how this could be wrong. We've tried pushing things to see, like, what do we need to do to make this different? But it just comes out beautifully that the bar looks like that. But it's very, like, if you just look in a different part of the sky, you might not see this very low metallicity part of the bulge.
Thank you.
Yes, one more question. Thank you.
Thank you very much for a very interesting presentation. Early on, you said what you don't see is as important as much as you do see. How do you, with deep learning techniques, how do you guarantee in the training program that you're not building in your own sort of biases into the system because you don't know what's there?
Yes, no, that's a very good point. I didn't really touch upon that. So we try to impart a bunch of our physical knowledge in the construction of these networks as much as we can. So for example, when we look at the spectra, we don't just throw, and we want to get the abundances, we don't just like take the entire spectrum and say like what is iron. We actually only allow it to use parts of the spectrum where we know that there are iron features. And so for oxygen, we would only use the part of the spectrum where there's oxygen features. So we're trying to make sure that we only use parts of the spectrum where there should be physical information, so where there's some sort of plausible physical connection, and then we're just using the deep learning as a way to kind of build a flexible model. But for example, with the ages, we don't do that. But there we just take the whole spectrum. So it could be that there's stuff in there about how it gets us age that we don't entirely understand. Like we're always worried that we're actually using correlations rather than like true like physical relations there. So yeah, for this we just have to test and just try to check that things come out independently, that there aren't like obvious correlations that we've used. But yeah, we try to, as much as possible, use our own physical knowledge as we construct these networks to get around and somewhat get around that issue.
Okay, thanks very much. I think we better move on to our next talks.
Thank you.
But thank you again for that very interesting presentation.